the go button. We are theoretically live, but as always, we require some kind of external validation to
Right.
confirm our existence. Hey, everybody, welcome to Monday Open Space. This week I've got Dr. Matt O'Dowd. Matt, how's it going?
Hey, Fraser. Great. How are you?
Good. You're right in the hot zone, man.
Yeah, this is the global epicenter, New York City.
Yeah, yeah.
It's this is why I moved here. This is the center of the world, man. Center of the epidemic as well.
little did you realize that you would be the center of a global pandemic.
I'd like to say that I predicted this, but uh, I knew interesting things would happen if I came here.
That's
At least
exactly
there's
it.
that.
Did you? I mean, do you have you got some kind of paper or something that you wrote saying that there will be a global pandemic and it will affect all of these major population centers?
No paper that I've ever written has turned out to be true.
Oh no!
Some of them haven't been disproved yet.
Oh, good. All right, all right. Well, like Einstein, it took what, like 100 years to finally prove one of his ideas, one of his final
Sure.
tests for relativity. So I think you've got lots of time.
Yeah, plenty of time. Yeah, some of them are pretty speculative. I don't think I'll have the same billion-dollar facility proving gravitational waves that Einstein did, but
Right.
yeah, there's yeah, I don't know. If I get just one, I'll be happy.
So, you are, of course, the host of PBS Space Time, and I mean, a lot of people know you for the nonsense, the the physics, astrophysics, just I don't way beyond my pay grade that comes out of your face. But you have a real job that you do that is not PBS Space Time.
That's right. I'm a professor at the City University of New York, which is currently on lockdown. Um,
Yeah.
I was on sabbatical anyway, so I wasn't
Okay.
teaching, but my colleagues are all trying their best to teach from home. It's massively challenging. But yeah, so normally when I'm not on sabbatical or when there's not a pandemic, I teach a couple of courses and I do my best to be a research scientist as well. Uh, so professor stuff.
And so, what specifically are your is your area of specialization?
Um, it's been more and more focusing on the most massive black holes in the universe, so-called supermassive black holes, and understanding how they grow and how they influence the universe around them, which turns out to be a lot, and finding different ways to peer closer and closer to those black holes, and which is a huge challenge. These things are impossibly far away, and by cosmic standards they're very tiny, and so it's part of the puzzle I try to solve is to learn how they work and how they rock the universe around them.
And of course, you were very fortunate that a team of astronomers from around the world captured the first image of a supermassive black hole just last year, although
Mm.
they've been working on it for a couple of years. And so we got just this incredible image of just this exact region right around the supermassive black hole. I mean, if you had access to that picture, I don't know, 5, 10 years ago, right? How would it have changed your thinking about your work?
you know we would have progressed the same way. I think what the picture did for a lot of people is um, we believed that black holes exist for a long time now. I study quasars, which are powered by these supermassive black holes, um, uh, and they're basically a more powerful version of the thing, the beast in M81 that's driven by that the Event Horizon Telescope black hole. And so for a long time, really since I don't know the 80s, we've been sure that nothing else could possibly produce the activity that we see in these quasars. Nothing could pull in material and accelerate it to such high speeds and such high energies to produce the crazy light that we see coming out of these these very distant astronomical objects. And there's been plenty of other evidence also. We see velocities too high close to these black holes. In the center of the Milky Way, we see stars orbiting, executing these crazy kind of slingshot orbits around some invisible central object that all of our best understanding of physics tells us must be a black hole. And yet, without having seen one, we believe it, but it's different when you see a picture.
Yeah.
It's like, holy crap, we weren't deluding ourselves all this time.
But I think you're exactly right that preponderance of evidence that had been built up to this point, especially like watching these stars whip around some invisible region like they were comets or like they were planets on these incredibly eccentric orbits going around nothing. Like, at a certain point, if it looks like a duck, quacks like a duck, right? Like if it's not a black hole, if it's not a region of mass compressed down to this enormous density, then whatever it is effectively the same thing.
Yeah. And I think this is a really nice example or illustration of where of this line that there exists between seeing with your own eyes and what you would call direct observational evidence versus inferred evidence or seeing indirectly. And in science we can be so sure because so many different lines of observation lead to this one consistent conclusion that we could be more sure than if we'd seen with our own eyes, because our eyes, of course, can deceive us. And when you look at something directly, there are many processes. You're not touching the object with your eyeball. There's stuff that happens in between. That there's the interpretations of your brain, and we know that the brain can trick us. And so I think when you really understand the care that goes into certain sets of observations that lead to scientific conclusions, I think in a sense we do see these things directly. We see them with our scientific eye, if you like, and this is the reality of black holes. I think is a good example of that, and I think we saw it very clearly scientifically before the EHT picture ever came along. Nonetheless, it felt good.
Yeah. Well, I mean, you can extend that concept, though, to some of these other mysteries that are happening in cosmology today. I mean, it's the same idea with dark matter and less so dark energy. But I mean, at this point, astronomers have seen dark matter many different, completely independent ways and confirmed its existence by every test that they want. They know it's there. They don't know what it is, but that's someone else's problem, right? That's problem number 2. At least be sure that it's there.
Yeah. And there are multiple consistent lines for dark matter.
Yeah, and so I mean, I don't know what the feedback is like for you, but I get this really emotional response from viewers just saying, like, I don't like it. I don't know what it is, and I don't like it. Yeah. And it's very weird to me because this is just another mystery. There was all kinds of mysteries that came before. And when you were in the middle of the mystery, it felt weird and destabilizing and confusing. And yet here now, when you come out the other side, you're like, okay, now I know why the continents fit together. Okay, now I know why the sun shines, etc. There is closure. But I think that for some of these ideas, I think we just got through that for black holes, but we're still in the middle of it for dark matter and even more so for dark energy.
Yeah, well, we'll never take a picture of dark matter, so that's going to be a tough one.
Yeah.
Although maybe some doubters will believe it if we create it in a particle accelerator or or who knows what. Dark energy, perhaps even trickier. I know in a way, we, as scientists, we should admire this impulse to skepticism, right? Like, be skeptical until you have the evidence, right? I guess here maybe the problem is in scientific literacy, and so people may have the right attitude, be skeptical without evidence, but they haven't had the benefit or privilege of a scientific training, even if it's a really basic scientific training that you should be getting in high school, to be able to assess these new types of seeing and knowing.
Yeah, yeah. I mean, I think that's a great point, that when a person comes at some topic and doesn't like it, I think it's definitely important to just understand their entire framework of thinking and what method, right? But if all they can get down to is, I don't like it, it's unsad. I mean, you'll hear scientists say a similar version of that argument as well. I find it uncompelling, I find it unconvincing, whatever. So it's not like it's just, it's in the lay audience as well. So you pick a lot of very complicated topics that I wouldn't touch with a 10-foot pole. And so I made fun of you earlier, that the stuff you say is nonsensical gibberish, but of course it is. You are a astrophysicist. You have a deep scientific understanding of these underlying principles, more so than I do. And you do a great job of making these concepts really understandable, but not making them wrong. So how do you walk that line?
I mean, I would say not always successfully. I think, we certainly get plenty of comments about, love this episode, didn't understand a thing. But if you're enjoying it, then great. That's also good. Apparently, some people love falling asleep to Space Time.
I've heard that from my shows as well. Yeah, clearly we're doing this other service.
It's because we have very soothing voices.
That's what it is. Yeah, yeah. Exotic foreign accents as well.
Exactly. Yeah. Exactly. Yeah, we could start ASMR channels easily. Anyway, we're not going there. So when I do get it right, or when we get it right, I think it's not so much a trick, although I think I've gotten a lot better at it over these years. But the initial secret was just having a little more faith in the audience. I think, we wanted to do a show that went deeper, that, we thought of it as, astrophysics for people who had graduated from the, 30, 40 years of Let's Make Science Fun, which had preceded this decade. And the school of Let's Make Science Fun was great, but a lot of people have just absorbed so much of that. They have this incredible kind of latent, knowledge that's insanely broad. And so we wanted to do something for these people, but also we wanted to do something that we would enjoy doing, and that felt new. And we thought we would get a handful. We thought it'd be enough to be worth doing. It turns out, to our great gratification, that there's an enormous number of people who are very hungry for a sense that they're kind of getting the real story, if you like. That they're being told, the stuff as scientists think about it, and I don't think we even have to get it perfectly right in terms of walking that very narrow line. As long as we're authentic and honest, and that's what we really strive for. We strive to just to cut the bullcrap, really, and really try to tell some of these scientific stories in the most honest terms. And I think people have incredible, bullshit detectors, honestly, and really know when they're being talked down to. And so
Yeah.
we like to just talk to people as though they're us with less time wasted going going through onerous physics degrees, and that seems to have paid off enormously
Right.
well.
There you go. You just saved them 12 years of misery.
And it was awful.
that's that's a time saver. But I mean, have there been topics, or are there still topics that you're punting, that you're just kind of going, oh, I just can't, nope, I can't. Some are, like, are there ideas that are so mind-bending and amazing, and yet they are so difficult to describe that you haven't been able to take a crack at them yet?
For sure. Um, there were, and there have been all along, and we've ultimately taken our shots. We tried string theory, which got some good reviews and some other reviews, from string theorists,
Yeah.
and uh, we never quite got to M theory, so that's there still. And I've been putting that off for a while now because, like, I feel like I just want to really get that one right,
Yeah.
and it's going to take, every time I dive into this, or if I'm working with another writer or researcher, it just, we bury ourselves for a while, and it's yeah, it's a hell of a deep dive.
Yeah.
Uh,
I mean, I know the feeling for, for me, there are topics that are, I mean, a lot more fundamentally, you'd have much easier time with them. And yet I feel like the closer you get to something that you have to be very specifically correct about, I find it just becomes orders of magnitude more complicated to make sure that you've dotted every I and crossed every T. And you're like, is this wrong? Is that wrong? Is this wrong? Am I saying this wrong?
yeah,
And I'm sure for you, as the number of people who actually know what's going on declines, they're more aware of your attempts to describe their work and
mm, mm.
poke out of the,
Yeah,
and come
yeah.
by to slap your wrists.
It happens. It definitely happens.
Yeah, yeah.
Yeah, and I wish we could do more due diligence. I mean, we do our best, but yeah, stuff still comes through. Uh, Wrong things,
Yeah.
less often wrong things, but sometimes we just miss key stuff, and you know, often we end up just going back and doing another episode and trying to squeeze it in somewhere
Yeah.
else. But
Do you get a feeling that sort of the overall educational level of the entire audience is sort of growing in this way that's allowing you to attempt more complicated topics with less, I don't know, like build up?
that's the hope.
Yeah.
I mean, everything builds on something else, for the most part, and it's like, well, it's the story of science. We stand on the shoulders of giants, to see further, and every episode ends up standing on previous episodes to some extent. It's been a fun puzzle, actually, because the YouTube way is, I mean, originally it was like 6 minutes max, but we stretch out. But even doing something in 10 or 12 minutes is super challenging, as I'm
Mm-hmm.
sure, and trying to, like, there's this kind of minimum amount of words that in which you can possibly express or teach a concept. Um, and so as we go on, we have to rely more and more on previous episodes if we're going to
Yeah.
progress that. And so there's people also joke about the number of times we say, go and watch this episode before you continue or whatever. It's,
Yeah.
I don't really expect people to do that, but you can watch it after.
Yeah, I know the feeling that it's funny. You know, my earliest videos were exactly that. They were 3 minutes long. They were 4 minutes long, and now I can't for the life of me write an episode that is shorter than 12 minutes long or 15 minutes long. Like if it's a piece of breaking news, maybe I can pack it down to 9 minutes. But and it is not me trying to game the YouTube algorithm. It is me, I think, just getting better at telling the story at a level of depth that I think that it deserves. And so I think when I look back on my older videos, I feel like let's make science fun. Let's say a thing that you already knew, as opposed to now, my goal is to say a whole bunch of stuff that nobody's ever, that no one else is talking about, that is going to be brand new and fresh for the people that are watching this, because you're going to get the same information again and again and again everywhere you go. But
Yeah.
yeah.
And it has to be fun for us. We have to feel like we're doing something worthwhile and
Yeah.
new and it's I know it's a two-way street.
Yeah.
We'll see. I really hope that people learn things, but one thing that is true, regardless of how much people retain, is that I'm sure both of us have sent many people back to school. We've inspired. I don't know if you've got comments. We get a lot of comments like this. Yeah.
Yeah.
So it's amazing.
Yeah.
If nothing else, we've inspired people to become STEM professionals of some sort or other. Most of them won't become astrophysicists, thank God. But the education will serve them extremely well, and the world, I'd like to think.
Yeah, absolutely. So this is also an interactive experience, and I know we've got a bunch of questions, and I would love to throw some of these questions your way. So from IRI, how could you build a quasar lens?
Quasar lens.
Mm-hmm.
All right, I'm going to try to interpret that in different ways. So I study quasars using gravitational lenses, but the lenses that I use are giant entire galaxies that happen to be along our line of sight to the quasar. So the light from the quasar kind of bends around the intervening galaxy and comes back to us via multiple paths through space. And so you see multiple separate images of the same quasar because you're looking along these kind of like this sort of funhouse mirror sort of situation. And in this way, you can massively enhance the power of your telescope because you have an extra, 200,000 light year wide lens attached to your telescope. It's a messy lens because it's made of stars, but that's its own thing. So the quasar itself, so the supermassive black hole bends the path of light from the accretion disk, and I'm sure many people have seen the movie Interstellar, where the gargantua black hole was beautifully rendered, and you have this image of the black disk, but then there's this bright band in front and then over the top. And what you're actually seeing there is the so-called accretion disk, which is matter that's superheated, screaming into the black hole, but in a disk around it. However, the light from the disk behind it, as it tries to escape the black hole, is bent by the curvature of space-time towards you, and so you see this lensing effect from supermassive black hole right now. And as it happens, we need to account for this effect, this general relativistic effect. And by chance, my graduate student sent me today his first simulations trying to account for this effect. And I wasn't even sure that it would be a huge effect for the types of observation that we're looking at, but initial indications are that it is very large.
And so is this this is an effect right now that you have to account for because it's messing up your observations, but could it be an effect that you could utilize to observe something else or something better?
It has information for sure. For example, it might help you learn the mass of that black hole. because the more massive the black hole, the stronger that bending. Uh, in the particular case I described, it's not going to magnify too much, but it's going to give you some extra constraints, I think, on the geometry, on what's going on in there.
Right.
Because all these things have to be consistent, right? So if you guess the mass of the black hole from the way the gas is orbiting around it, that's got to be consistent with the mass that you get from this lensing effect as well. And so, back to this whole idea of all these different lines of evidence coming together in a consistent way, makes us more and more sure of the evidence. But certainly the lensing effect of the galaxy and of the individual stars in the galaxy is hugely powerful. We can do an awful lot with that.
Yeah, there's I mean, even just with the Event Horizon Telescope, we're just really at the beginning of this idea. I mean, there's going to be more runs every year to make more observations. I've also seen some interesting proposals to put up radio telescopes that would fly into space and then join the interferometer, providing a much larger baseline. And you could take this right now, the ability to observe 2 supermassive black holes and expand it to hundreds. And start to see far more detailed images and regions around the surfaces and nearby area around these supermassive black holes. So like anything, I mean, it's like we got to see the forefront of it. We got to see the first just like image, but just you wait 10 years from now, 20 years from now, right?
Yeah, I have plans. With gravitational lensing, you can resolve the region around, smaller than the event horizon, and potentially with thousands of these guys. And yeah, a few collaborators and I have a plan to try to do this. It's going to take us maybe 13 years.
Right. And so, I mean, I guess, the long answer for that question is that you're using quasar lenses all the time. You couldn't do your work without them.
Yeah. That's right. It's so cool. It's so cool trying to understand black holes, a prediction of Einstein's general relativity using lensing, another prediction of Einstein's general relativity. It's a very Einstein universe we live in.
I always say
that guy.
that we, with dark matter, we don't know what it is, but we know how to use it as a telescope.
Yes, that's exactly right.
Yeah. So
that does most of the lensing in these galaxies.
Larry Beckham asks, Dr. Matt, do you have any doubts on cosmic inflation?
Yeah, good question. This is another example of something. I mean, far more so than black holes. No one's ever seen it. No one's ever even detected anything that you might call direct evidence. It's just the best model we have to explain a couple of things, which I could go through, but basically the fact that our universe seems so smooth and homogeneous on the large scale. It seems like the two distant horizons of the universe were once upon a time in causal contact with each other, but they're so far apart that even rewinding as far as we can to the Big Bang, they should never have been in contact. And inflation is the best story we have, but that's one that I would love to see a little more evidence on.
Mm-hmm.
And I hear that it's just so well accepted. I mean, I almost take the ubiquitous acceptance of inflation by cosmologists as another point of evidence in its favor, because surely they know better. But it's I would love us to see some of those primordial gravitational waves or something.
Right. But I mean, you've got this situation where you've got this theory of the Big Bang that works perfectly except for these problems. And then along comes another theory that fixes all of those problems and yet is brutally difficult to gather any evidence for it to be able
Yeah.
to add to that picture. But I mean, it's not impossible. I mean, we saw the attempt searching for the polarization of the primordial gravitational waves. You know, that was and then it ended up being wrong. But
Yeah.
but it was, you know, it was an attempt to try to get
In principle.
in principle to get at that answer, and maybe a future much better observation will make this happen. You
But
know,
there is evidence. There is what you would almost call. I mean, to believe in a new theory, the theory wants to make a prediction, and then you want to go out and see that, right? But one prediction that cosmic inflation does make is what you call the power spectrum of the cosmic microwave background fluctuations. Okay, so inflation predicts that the blobs we see when we look at this afterglow of the Big Bang, so we see the afterglow of the Big Bang everywhere. It's extremely smooth, except if you look closely enough, there are blobs. Okay, and those blobs are just tiny fluctuations that existed in those very, very early hot dense times right after inflation, if it happened. And inflation predicts that exponentially expanding space-time that existed before the Big Bang should have been producing copious particles by quantum processes, you know, virtual particles appearing and annihilating. And those particles, according to inflation, are responsible for these blobs. When inflation stopped, there was this distribution of energy that was a little bit more here, a little bit more there, depending on where those totally random particles were at that early time. But inflation can predict the sizes of the blobs, how many small ones there should be compared to big ones, and inflation predicts, you know, what we call a power spectrum, basically that it's what we would say is scale independent. So essentially there are as many big blobs as medium blobs as small blobs, and so this scale independence is a prediction. And we look at the cosmic microwave background blobbiness and the power spectrum, and that's exactly what we see. It's scale invariant, and we also see that in the distribution of galaxies on the sky, the galaxies that would later form from those blobs. So there's at least one. And that's I would like to, honestly.
Right. But couldn't that also be explained by an incredibly unlikely chance?
I think it would be, I think it may be explained by something that's not inflation. Like, you don't need inflation necessarily to get a scale invariant power spectrum. So there might be another story that gives you that.
Yeah. Just highly unlikely. Like I'm just saying, like, you know, we run the universe simulator a ludicrous number of times, and one of them might give you what we see, but that's not what you would expect.
Yeah, when you see something, when you see a pattern so strong, then you want a cause.
Yeah.
And unless you can invoke the anthropic principle, which a lot of people do not like doing, then you want to find a reason why. That's the case, and inflation works in a lot of the. I mean, that's the one major prediction that I feel that it's made, like the post-fact prediction. The other stuff, it was designed to give you the smoothness and the flatness of the universe, but then can it make predictions beyond that? So far, I would say there's one prediction that it's made.
Was a Poet asks, how taut is space-time if space bends and gravity can warp it? So, could it snap?
So it should be infinitely flexible in that sense, infinitely extendable. I don't think there's a limit to how much you could stretch space-time. But who knows? Once we start building warp drives, you get one of the Star Treks. They realized they had to limit themselves to warp 5 or whatever because they were tearing
Yeah.
cracks in the fabric of space-time. So we're not there yet. As far as we know, according to the Einstein's picture, it can be stretched without limit, and inflation did so. Crazy exponential expansion. But just because it doesn't snap doesn't mean it's not taut. So when you think of that's in physics that means how hard is it to stretch something. It's actually very hard to stretch space. You can measure the amount of tension in space by how much energy it contains when stretched. Okay, so if you think of a spring, like a loose spring, you can stretch it easily, and then it will flick back, and big deal. It's not going to whip your finger and hurt you. But if it was a strong spring, and you stretch it out and you let go, you could have a bad time because there's a lot of energy held in that stretch. Well, space is quite taut in that sense. Tiny amounts of stretch contain an enormous amount of energy. And that's, apparent from gravitational waves, for example. Like if you think about the amount of stretching of space that is caused by a typical gravitational wave from emerging black holes that pass through the Earth, they move, like they change distances by, what is it again, 1 part in 10 to the power of 23 or I don't know, something, a thousandth the width of a proton over 4 kilometers, I think, is the stretching. But that still is an enormous amount of energy. These albeit in some cases a billion light years away, these giant black holes of like 30 times the mass of the sun merged, and in many cases release something like 20% of their mass or more as pure energy. That energy is just in the stretching of space. Now, if we can see these things, they're bright. If we could see these things in light, like for example, if they're neutron stars, then they're bright. But if we see them in gravitational waves, they're as faint as you can imagine, that tiny stretching of space from a colossal release of energy. And so that's like if you have this very heavy spring, it takes an enormous amount of energy to stretch it a thousandth the width of the proton. So
it is an absolutely incredible feat of science and engineering that we're able to detect them at all.
Oh, so amazing.
Yeah. And it's funny when you look at some of the gravitational wave observatories that are just on the design board right now. There are observatories that are going to have arms that are 40 kilometers long. Space-based interferometers, theoretically, they're going to have arms that are 10,000 kilometers long, possibly even ones that will be the length of like an astronomical unit. And so you can imagine getting to this point where we were lucky to see one, that suddenly we're able to see gravitational waves in every single gravitational wave event, every colliding neutron star, every black hole merger, even the primordial gravitational waves from the beginning of the universe, all visible all the time.
Maybe. Although it's going to take more than just building bigger interferometers, because the size of the interferometer determines the frequency of the event. So build a very large one, build one the size of our solar system, and we'll be blind to merging neutron stars because the frequency of those merging neutron stars is too high. It'll see much larger things like merging supermassive black holes. So we have to. It's a multi-pronged thing. We definitely want the very large observatory so we can see across the frequency spectrum of gravitational waves. But we also need to, it's not we can't just hit it with a hammer. We need to build more and more sensitive 4-kilometer long interferometers, and we need to so we need to understand the minutiae of the mirrors, and we need to employ bizarre quantum mechanical states of light. We need to use squeezed light in our interferometers. All these really fascinating things, actually, in order to get more sensitivity, and also just more of them is also helpful.
Yeah. I got a question from LK Raider over on Twitch. Are we stuck in particle physics until we get a larger collider? What are the paths forward? I know particle physics isn't precisely your specialty, but I mean, we are at a crossroads at this point.
Yeah, it's a tough one, right? I mean, the Large Hadron Collider, it's not the size of the planet, but it's the size of a country, and things don't quite scale up linearly. You can't just build one the size of the planet and expect to see all of the particles. We don't know how we don't know at what energies those particles are. The larger the collider, the higher and higher the energies you can see, and we'd expect to see. So the LHC is sensitive to a certain energy range, but we don't know if we build a bigger one if we'll see the particles that the LHC couldn't see, because not having seen them, we don't know what the energies are, and yeah, so I think we should keep building them, but I wonder. We do need to be pretty smart about the investment. I think
I mean, at this point, people are starting to, they don't have any specific thing that they're looking for. I mean, the plan now is just smash and see what happens.
Yeah, I mean, I think a lot of people still want to prove supersymmetry and find those supersymmetric particles that we'd expected to see by now, that must surely be at higher energy, because surely supersymmetry is true. So some would argue that we'll get that they're lurking just above our mass range, but it's a crazy large investment. It's so many billions, I guess. But people do smarter things. I think there are other ways to attack these problems. Cosmic ray particle physics, so astroparticle physics, is it's not as controllable. You have to wait for those cosmic rays, but those the universe is a pretty awesome particle accelerator, and can create much higher energy particles than our particle accelerators can. Not as controllable, but
right. So Vovacat17 asks, what is your favorite, best, unrealistic, bad science sci-fi movie?
Well, we talked about Interstellar. No.
For bad?
Well, no, it was fine. The depiction of the black hole was spot on.
Especially inside the black hole. I mean, really, just that idea of there being a library is...
It cannot be refuted. There's no way to show that that's not the...
Yeah.
Yeah, that was okay. My favorite bad... I like the good ones. Damn it.
Yeah.
You tell me yours, and I'll think. What's your favorite bad?
So I'm a lot more forgiving on this front. And I'm sure it's the same way that people are towards the way we do our videos, which is that if we, okay, all right. So here's my perspective on this, which is like, if you want to come up with a warp drive, you want to go fast. Like if you're trying to just tell a story and you need a way that you can get across the universe in a very short period of time, or use a Stargate, then do it, right? Who cares? But if you're going to have Optimus Prime reach out and grab a person who's falling out of a building and not essentially have them the equivalent of hitting metal, then you should have taken a second and just thought about how to minimize the amount of G-force that happens on the human body over a certain amount of time, right? And
And that's all
so,
it takes. Just a second. Just hire a physicist
yeah.
to consult. We don't charge much. We don't have much.
Exactly. Yeah. Yeah. And so I think that, I mean, it feels to me like, and I've brought this example up many, many times, that it's like there are so few examples of stuff that's great, that really nails it, that really the rest of it is all kind of the same. You know, it's all wrong, just wrong. And so, you have just these few shining examples, like The Martian, mostly, Interstellar, mostly, and The Expanse. I'm loving The Expanse. Mostly, they nail it. And in fact, use science to have some interesting scenes. Are you watching The Expanse?
I've watched the first season.
Okay.
And I feel like there may be plenty of home time ahead to watch more of it.
Yeah. There's a scene in season 3 where they're in a ship and someone left a toolbox open and the ship is having to do high G course corrections. And so the tools are floating around inside the cabin, and then every time they have to change direction, the tools go in a different direction, like bullets inside the spaceship. It's really clever, right?
Yeah.
So it's a thing that you wouldn't think of unless you were really trying to think about how the physics work. So the bad stuff I just forget about it. I don't even think about it anymore.
Well, let me answer then. So, not movie, but series also. We've been watching old seasons of Doctor Who. Okay, now Doctor Who, the physics is terrible. the site, it's pretty bad. But it doesn't pretend to be anything else. It's delightful. So the reason it's so great, I think, is that it just feels like old school science fiction in the sense that it's forward looking, it's optimistic, and we were wondering why we liked it so much. We were watching something else. Devs.
Mm-hmm.
Are you aware of that?
I'm watching Devs. Yeah.
Yeah, it's very good, right? But it was getting us down, and in that the physics is good, right? They talk about or there's good discussions of physics because there's discussions of Everettian quantum mechanics versus Copenhagen and de Broglie Bohm, and what these mean about the nature of reality, and so there's these quite high end discussions of this stuff. And don't get me wrong, it's very good, but it was getting us down because it's kind of dark. And in these dark times, we realized that, all right, we need to take care of our mental health a little bit. What do we need? We need we need to rewatch season 6 of Doctor Who, season 7 of Doctor Who. Matt Smith, and it, I think science fiction has got quite arty now. The Expanse is quite dark also.
Mm-hmm.
I think this is a much cooler way to do science fiction now. But I think once upon a time, science fiction was just much more, I don't know, just upbeat, optimistic, and Doctor Who is great for that. If you're feeling, like you're not sure what the point of existence is because you've been locked in your apartment or whatever.
Yeah.
The doctor will tell you what the point of existence is.
He'll fix you. Yeah, we've been watching Picard, and we've been watching old episodes of Star Trek and the animated series, which has been just super fun to watch. That I don't know if you've seen the old show Star Trek and then the animated series. The animated series, it's all the same voices, but they are but they're all animated, and so they can have these weird. They're meeting these weird aliens, right? These aliens that are vegetables, and these aliens that are in these gigantic ships that are a billion years old and are formed of crystalline structures, like sets that they couldn't have built back then, with characters that they couldn't interact with, and yet they're able to explore all of these ideas. Some just in a terrible way, but it's a there's some awful episodes, but there's some really good episodes, some really inspired episodes, and you sort of say, oh, before really good special effects was available to them, an animated show was actually a great idea. And it sort of, I felt
Sure.
like every television show should do an animated version. Every sci-fi show, there should be an animated Doctor Who. Maybe
Yeah.
there is, right? An
I think
animated
there might be.
Firefly.
Yeah, totally. And Star Trek, I mean, original Star Trek has such horrible special effects
Yeah.
that it makes a lot of sense
Yeah.
to animate that. Doctor Who is worse.
Yeah. All right. Let me see if I can get another question here. So there was one here. Arjun asks, so how far should we go into the science of things that cannot be presently or ever observed, like the strings in string theory? Or should we just wait for more data?
Yeah, this is a tough one. And this is a question that we are going to have to answer as a civilization because the universe is under no obligation to make its, every next layer accessible to every next generation of scientists, right?
Yeah.
It may take many generations before the next layer is accessible by our technology. And so what do we do in the meantime? Do we just declare everything that we try to understand about those deeper layers not science because they're not currently testable, even if they're in principle testable in the future? And there may be aspects of reality that like, for example, direct observation of a graviton. There's no conceivable, experiment that can do that. So we can't just declare them not science because, some pretty reasonable ideas of quantum gravity demand something like a graviton. So I think we do need to start to rethink what we mean when we say, is it scientific? Is it testable? The whole, I guess, Karl Popper-esque idea of this observation-driven science definition of science. Maybe need to be a little more flexible than that. For example, we can talk about when math converges in such an uncanny way as it does, or as a string theorist would say it does in string theory, but also in other ideas. Is that a type of evidence?
Mm-hmm.
Right. So I think we are, particularly particle physics is reaching some sort of crisis point.
Mm-hmm. Mm-hmm.
But you're not just going to stop, because if you stop, you're not going to be building the experiments or thinking
Right.
about how to cleverly get around the impossibility of the experiments. And
Yeah.
I'm reading Paul Dirac's biography at the moment, and he was the ultimate theorist. He was the theorist's theorist, and famously predicted the existence of antimatter purely from his equation. And so I'm sensitive right now to the fact that you really can glean truths about the universe just from these mental exercises.
Not to mention everything that Einstein did. I mean, I think part of it though is like I get this pushback, and I'm sure you get a similar flavor of comments and questions on your videos, which is like, why are people thinking about Dyson spheres, or why are people thinking about how to go to other stars? It's just not practical, etc. Right? And my response is, hey, we're just thinking. Like we're just sitting here, we're thinking of ideas, and nobody's getting hurt. So you can't constrain my imagination, man. And I think it's an extension on that, which is like, if all a physicist is doing is sitting down and putting, pen to paper, or LaTeX to computer screen, um, and they are exploring in the way that mathematicians have always explored, and 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 we don't know where those paths lead. I think definitely if you look at like a lot of really tangible resources are being dumped into one thing or the other, and it is causing other very useful things to not happen, then there's a conversation to be had there, right? No one is actually building an interstellar starship. All we're doing is talking about different ideas because it's fun, man. So I think that
And
no,
sometimes they pan out massively and change the entire world.
yeah,
You
yeah,
know,
yeah. And I mean, even
like
string
quantum
theory.
mechanics.
Yeah, I mean, even string theory, we don't obviously have any way to really test it today, but string theory has delivered many useful mathematics that has practical applications in other fields of work. So it hasn't been a complete waste of time so far. It has actually been a very functionally useful field of mathematics that has, other uses. But, could the lifetimes of 200 mathematicians been used for some more, you know, useful task? Who knows?
Well, and also you can't, you have to pursue these paths before you know whether they're dead ends,
Yeah.
right? There's no guarantee that any particular promising path you pursue is going to lead you where you need to go, but you've got to try them,
Yeah.
right?
Yeah.
And even if we just ruled it out, that's something. We constrained the possibilities.
Well, that's obviously what you want is you want to confirm the existence of your graviton or whatever, right? Or that your axions are your dark matter. But the other way to go is to just start ruling out until the thing is impossible. And that's your second best way to approach it if you can. So that might
Yeah.
be for a lot of these ideas, that's the way they're going to have to get ruled out. The math holds observationally. They've searched in every corner and they don't exist. When you lose your car keys around the house somewhere, and if you looked everywhere, then maybe you don't have a car. It's the only
Maybe
possibility, right?
that's a beautiful analogy.
Yeah.
It
Yeah.
works in so many ways.
Yeah. So, all right, I got one last question for you, which I think is totally different, which comes from Anakim Luke on Twitch. I have a boring question. I'd like to know about time management between Academy and making PBS Space Time. So
Oh
how
wow.
how do you manage your time?
Uh, so
See, I just have one job. You have
yeah,
two.
I've located this secret extra reservoir of hours that I don't know if everyone's noticed them, but they're called evenings and weekends, which is to say I work too hard.
Yeah.
Uh, yeah, it used to be more ridiculous, and uh, it was I just worked a lot. Um, Now I still work a good amount, but I'm much faster at writing scripts. Um, I have just quite a store of just crap that I've learned now. So when I started PBS Space Time, my particle physics was pretty bad, and now it's less bad. And all these other
Yeah.
random paths we've walked down, and uh, so it's a lot quicker.
Yep.
I'm a lot quicker in front of the camera. That used to take a long time. I
Mm-hmm.
used to. It's harder than it looks, as I'm sure you know.
Yeah. Yeah.
The idea of staring at this black lens and trying to emote at all, pretend that's a that you have uh, any feelings towards this disembodied thing,
Right.
while reading, because I'm typically finishing writing the scripts minutes before we shoot, and so there's no time to remember anything. So there's a teleprompter. So yeah, that now that's much faster than it used to be. The first episode it took us like 8 hours to film it, and just because we had to do it again and again and again. And I came back the next week, and my producer Andrew Kornhaber said, "Matt, we got to just refilm everything. It's unwatchable."
Oh no.
How bad can it be? And I couldn't watch more than 30 seconds of it. It was awful.
Yeah.
So that's faster now. Yeah, but in the end, it's hard, but I get better.
Yeah. The thing for me that has made me a much better science communicator is doing the live work. So
Really?
yeah, absolutely. Being in real time, answering questions, nothing focuses the mind in that way. And I think that, like, if you go back and look at before I started doing the question shows and now, I'm a vastly better science communicator than I was back then. And it's mostly, at this point, I've on my question shows, I must have 1,000, right? Questions. No, let me think. Yeah, more than 1,000 questions answered. All the live stuff, an hour a week of just me answering questions. It has been just so good for my brain. So I
Great. Wow.
I highly recommend turning on the camera and live streaming. And I know your fans would love it as well. So, in case you
All
do
right.
find like another dimension that offers some sort of time, then, I highly recommend it.
Like a global
Like a
pandemic
global
in which
pandemic that forces you to stay at home. Yeah, something
oh,
like
we
that.
we have we have moved all of our filming equipment to my apartment now,
Oh, great.
so that for the foreseeable future I'll be filming in my apartment, so it won't be green screen, which is going to be different.
Yeah,
We'll see how that goes,
yeah.
but it's sitting there. I guess I could use it for something else.
Yeah, absolutely. Well, Matt, it's been an absolute pleasure talking to you. Of course, if people want to find out more about what you do, where should they go?
Well, come to PBS Space Time on YouTube first and foremost. That's where I talk about space. Um, you know, my other social media are very spotty, so I would just come to Space Time.
Yeah,
I
no,
have a website.
I
I
agree.
think you
Um,
can Google me. I'm Googleable. You'll
yep.
find my website.
Yeah, Twitter is just a place of sadness and grief and anxiety for me these days. So, I try
Mm,
not to spend as much time on Twitter as I or any of that other stuff as I can. I limit
yeah,
I'm really trying to limit my news intake to just a couple of minutes a day just to make sure that nothing really has gotten away from my mind. But apart from that, I find I can rabbit hole and spin my wheels all day long and not get anywhere.
yeah,
So, yeah.
yeah. It's a good habit.
Well, again, you're in the epicenter of this. You're in the hot zone. So, dude, stay safe. Stay inside. Definitely make those green screenless episodes.
For now.
All right.
Absolutely.
All right. Well, take
And
care, Matt.
everyone stay safe.
Yeah.
See you, Fraser. Thanks very much.